Hey there, Calc folks, back here with another video lecture in our what has been our series of lecture on multivariable functions. We are discussing the partial derivative currently and looking at some of its application in our work. My last video just covered using the partial derivative of a multivariable function to help calculate an implicit derivative. Looked at the case of implicit differentiation. Right. However, we're going to take that a little further now, and I've been highlighting this topic since the start of partial derivatives, and that is looking at what we call a directional derivative. We're right there. Directional derivatives is actually going to be my next video. But in order to calculate that directional derivative, we're going to need to first define what's called the gradient of a multivariable function. And that is what this set of notes gets into. Here we talk about the case for the gradient of a multivariable function. All right. To begin with, to calculate the gradient, I am going to have to introduce an operator known as the del operator. All right. And I do that initially for z equal to f of x comma y. An operator can be applied to this function known as the del operator. All right. What I might point out a little further is this is done in the process of finding the gradient of of multivariable function f. All right. The del operator, when we talk about the del operator, is just itself a vector operation. Now, it is denoted as this vector seen here. This is called the del vector. That upside down triangle is actually the symbol we call nabla, N-A-B-L-A, nabla, right? When we see that written with the vector notation over top of it, it is highlighting what we call the del operator or the del vector, all right? Where what it is what's known as a vector operation. It's the first operation we encounter that's actually known as a vector operation. It's an operation that applies itself in the form of a vector. For x comma y contained in two-dimensional space, the del operator is just the two-dimensional vector given by the partial with respect to x for the first component and the partial with respect to y for the second component. And for x, y, z contained in three-dimensional space, the del operator is itself a three-dimensional vector operation where each component is made up of the partials for x, y, and z respectively. And that is what we do note as the del operator is a vector in n-dimensional space with components describing the corresponding partial operators for the variables defining that space. Right? It is a vector whose components are comprised of the partials, right, defining that space. Partials for the variables defining that space. If x and y define two dimensions, it's filled up with the partial with respect to x and the partial with respect to y. If it's x, y, and z defining that space, well, the three-component vector operation. All right. Let's see where I go from here. Now, as noted, the gradient requires the use of the del operator, and that is the next thing I define here. Right? For a function existing in n-dimensional space, the gradient vector operation, right? The gradient vector operation given by del of should really call this what? Not the gradient vector operation. Let's just call it the vector operation. Right? The vector operation, right, defined by the del vector, we'll say here, contained in n-1 dimensional space, can be applied to the f in n dimensions in the form of a scalar multiplication denoted as del of f. Right, denoted as del of f, right, indicating, or we might say here denoting, what is called the gradient of f. All right. So for z equal to f of x comma y, the gradient of f, z equal to f of x comma y, contained in, this would be in three-dimensional space. The gradient of f is given by this vector seen here. Or I should really say this vector operation applied to the multivariable function f. Right? It is given by the del of x comma del of y vector, the del operator, multiplied by the multivariable function f of x comma y, which acts a lot like scalar multiplication. That del operator, right, this multivariable function will distribute itself, right, will distribute itself across the terms of that vector. It'll apply itself to this operator, and it'll apply itself to that operator. And what we will end up forming is this two-dimensional vector, right, made up of the partials of z with respect to x and the partials of z with respect to y. Right? That's all the gradient vector is, folks. All the gradient vector is a vector, right, comprised of the partials for that multivariable function it's being applied to. Right? If we were to apply it to the four-dimensional vector, w equal to f of x, y, z, contained in four-dimensional space, the gradient of f is going to be given by this seen here. And what we do see that it is going to be a three-dimensional vector of partial operators applied to our four-dimensional function, which is going to produce a three-dimensional vector result made up of the partial derivatives of that multivariable function. Right? This is the calculation of our gradient in two dimensions. Well, I should say for a three-dimensional surface. This is our calculation of gradient for a four-dimensional hypersurface. Right? The gradient is essentially a description on that surface made up of a vector description on that surface made up of the, I should be careful, on that surface, I should say for that surface, right? Made up of the partial calculations for the independent variables of that surface. Right? Respectively, here for the three-dimensional surface, we have the two-dimensional gradient seen here. For the four-dimensional surface, we have this three-dimensional gradient seen here. The gradient always exists in one dimension less than the function. Note the gradient of f contained in r sub n is a vector. A gradient of f contained in r sub n is a vector in r sub n minus 1. What it actually exists in is what's called the domain of the function. All right, it does exist down there in that domain of f, with components described by the partials of f. Right, in the end. All right, folks, if we scroll down, I do believe we see an example of the gradient. Right. We might consider finding the gradient of f for f of x comma y equal to x squared plus xy cubed plus xyz in value. Right. We might consider finding the gradient, right, given by this notation for this four-dimensional surface seen here, folks. All right. Now, as we had noted, all the gradient is going to be is a three-dimensional vector, a vector that really exists in the domain of this four-dimensional surface described by x, y, and z, right? Made up of the partials of that function with respect to x, y, and z. Right? And it's not hard to see what your partials are. With respect to x, it would be 2x plus y cubed plus yz. With respect to y, it would be 0 plus 3xy squared plus xz. And with respect to z, it would just be 0 plus xy, or just xy in value. Right? If we were to set this up, in this case, we will have that del operator applied to that multivariable function, where that del operator in three-dimensional space is made up of the three components for the partial operators with respect to x, y, and z, respectively. It'll apply itself with respect to x to this multivariable function for our first component of the gradient. It'll apply itself with respect to y, right, to the multivariable function to form our second component. And it'll apply itself to z to the multivariable function to find our third component. And I did roll through those with you. The first one would be with respect to x, and that does produce 2x plus y cubed plus yz. The second component would be with respect to y. That would be 3xy squared plus xz. And the third component would be with respect to z. And that would simply be x times y in value. Right? 0 plus x times y in value is what we get if we took the partial of that with respect to z. All right? This is the three-dimensional gradient describing this surface up above. All right. Now, what do I mean by describing this surface? There does exist an interpretation of the gradient, which is mentioned here in the following two notes. First of all, the direction of the gradient at a location in F's domain indicates the direction to move within the domain at this location where the greatest increase in F will occur. If we were to put ourselves at any location in the domain of our function F, and we were interested in what direction, how should I change my x, y, or x, y, and z values? How should I change my domain values so that I experience the greatest increase in the output of the function? Well, that direction of greatest increase at that location on the surface is described, well, I should say the direction that you would move in to experience that greatest increase on that surface is described by the gradient of F. As for what is the rate of change in F in that direction, that is what's going to be given by the magnitude of the gradient. The gradient is a vector. The gradient has, well, vectors have two parts. They have a direction and they have a length. The direction tells you the direction of greatest change. The amount of change is actually described by the length. Now, if we were to look at the opposite of the gradient, seen here, The direction of the opposite of the gradient indicates the direction to move within the domain at this location where the greatest decrease in f will occur. If the gradient is the direction we move to go up the quickest in values of z, for z equal to f of x comma y, to go up the quickest in our output, I should just say, then if we turn around and we go the other direction, the direction described by the opposite of the gradient, this is going to be the direction that actually produces the greatest decrease, right, in the output of that function. How much we're decreasing by, right, or that actual rate of change in f would be described by the opposite of that magnitude. The negative indicating the decrease, the amount of change indicated by the absolute value of the gradient. All right? That's some interpretation. Let's look at that with an example. Say, consider the gradient for the surface 4 minus x squared minus y squared. Right? It is just going to be a two-dimensional gradient, right, found by applying the del operator to the function f of x comma y, which when it applies itself to this multivariable function, your first component of that vector operator will just be the partial of that function with respect to x. The second component will be the partial of that function with respect to y. And it does simply produce the gradient description negative 2x comma negative 2y in value. All right. So, at every value of xy in the domain of f, right, this domain described by the set of points x comma y contained in two-dimensional space, the greatest change on the surface will occur in the direction within the domain described by this location at any given xy coordinate. X would be substituted in there, and y would be substituted in there, and we would have a direction of greatest change. The amount of change, right, would be given by the absolute value of that vector, or, sorry, the magnitude of that vector, the length calculation. So, if we were to place ourselves at 1, 2 in the domain at that location, the direction of greatest increase in that function described within the domain would be in the direction of negative 2, negative 4. Substituting in 1 for x and 2 for y will produce the direction described by negative 2, negative 4. Right? That is the greatest rate of change on this surface, 4 minus x squared minus y squared, right, in the domain at the location of 1, 2. We would move in this direction. How much we would be changing by is by the magnitude of that, which would be the, square root of 4 plus 16. Or the square root of 20, which would be, 2 root 5 in value? And I do think I make that note next. As for how much f of x comma y, increases by, when moving in this direction of this, at x comma y equal to 1, 2, right, is given by that magnitude, which is, again, just like I said, 2 root 5. It is the square root of this component squared plus this component squared. All right. Now, what does all that mean? Well, let's look at a visualization of this, I do believe. All right. Well, first of all, I do take note whereas the direction described by the opposite, we get into the opposite interpretation here real quick. 2, 4 describes the direction of greatest decrease in the surface at that coordinate in our domain, where the rate of change in f in this direction at this coordinate is actually described by the opposite of that magnitude, negative 2 root 5. If this is the direction of greatest increase on that surface at the location 1, 2 in the domain, then the opposite of that direction would be the direction of greatest decrease on that surface. How much we're increasing by, or what is the rate of change in this direction? Well, it's 2 root 5. What is the rate of change in this direction? It's negative 2 root 5. Opposites of each other. Where now we have the visualization. Note the following visualization for this surface, where we do have the point 1, 2 highlighted on the surface and within our domain. Blow this up just a little bit. Right here, folks. Here is that surface. This is the surface 4 minus x squared minus y squared plotted in Mathematica. This is the location in the domain at 1, 2. You can see here we're at 1 on the x-axis and at 2 on the y-axis. At that location in the domain, the direction of greatest change would be down 2 with respect to x and right 4, or well, I should say here, in the negative direction 4 units with respect to y. In the negative direction 2 units with respect to x, and in the negative direction 4 units with respect to y, pointing at the end of that vector. All right. Notice the orientation of x, y, and z here. I did spin it around to kind of give it hopefully what I think is a clear illustration, right? We can see our point. We can see our point in the domain. We can see the vector that corresponds to it, right? If we are at this location, the corresponding location on the surface, this point, for this point in our domain, and we move in this direction described in our domain, that will actually place us on this path. Where I did try to make the curve or illustrate the surface in this path so that you can kind of notice that if you were to travel in this path through that point, that is the greatest rate of change. And we can say that kind of intuitively because it's the path you would take to reach the top of the hill the quickest. If you're at any point on that surface and you want to reach the top of the hill the quickest, you're going to go on whatever path has the greatest rate of change. And at that point, we would be on that path, which passes through, right, the very tip top of this surface. So that is the direction of greatest change. If we were to turn around and walk in the opposite of this direction, that would be walking down the path, down the surface this way. That would be the direction of greatest decrease. How much is z going up or down by at that location when we move in this direction? Well, it's going up by 2 root 5 units, or it's going down by 2 root 5 units, respectively. Right? That's all illustrated here on this surface for this example. Right? That is what we're describing with gradient. Gradient is this vector description that happens in the domain of our function that tells us if we were at this location in the domain and we wanted to see the greatest change in the output of our function, which direction would we move at that location in our domain? And what the gradient will tell you is that direction you would move in that produces the greatest rate of change in the output of your function. Here we can see that greatest change on the output of the surface would put us in the direction of, the greatest increase would put us right in the direction of reaching the pinnacle of this surface the quickest. Right? It would be the path to the top, right, at any given point, we might say. Gradient is related to grade, folks. In two-dimensional context, grade is slope, rise over run. If you were to place if you think about this being a three-dimensional hill, and you were to place yourself on that hill at that point, you would be asking yourself, what is the grade of that hill? What's the slope of that hill at this point? How much is the hill pulling me downward, and gravity pulling me down, in what direction? If I was to pour water at this location, where would that water flow? Right? Or if we want to reverse that context, we're in the context of fire season, right? And if you know anything about fires burning through landscapes, the worry is burning uphill. They burn uphill the quickest, right? They're going to burn, without a wind, they're going to burn up lighting things above them on fire the quickest. So we might say this grade also describes the direction for what might be the quickest rate of change in a path of some fire on some three-dimensional landscape, right? Absent wind and whatnot. Wind certainly would push that off in different directions. Right? But it's grade. If we were to drop a ball, which direction would the ball roll? Well, it would roll down this path. Right? It's grade. And those are some interpretations of that grade. Right? This is a description of grade in 3 dimensions. We've had a description in 2 dimensions for slope for quite a while. Now this is 3 dimensions. You can look at this also for hypersurfaces in 4 dimensions and beyond. All right. There's one other interpretation I want to get into here, folks. Just it's quick. Not much left to give you here. It goes along with this illustration. Excuse me. Lastly, the gradient in the domain of f at a defined coordinate of f is orthogonal to the level curve passing through this coordinate in the domain. Note the following illustration for the previous case, where the level curve passing through this coordinate is illustrated in both D, the domain, and, I should say, on the surface. Right? And where the direction of the gradient is illustrated orthogonal to the level curve in the domain, along with the corresponding direction of tangential behavior at this coordinate. Now what I'm describing is this illustration seen here. Here, this is our illustration from before. Here is that point in our domain down here. Here is its corresponding location on the surface. We saw that this path was the direction of greatest change given by the gradient. I have changed its color over to this green vector direction seen here. I did not give the full length. I just went ahead with just the direction. All right? This is just highlighting that direction, not necessarily the length. What this property deals with is specifically direction and doesn't really have much to do with length. And what this property says about this direction is that this direction is orthogonal to this level curve, seen as the circle, right, down here within the domain. This direction meets at that point on this level curve at a right angle to the tangential behavior seen by this green line. Right? These two lines are our tangential and orthogonal directions at that point on the level curve, which corresponds to this point on our surface, right? Where this is that level curve's cross section, right? And this is the path of greatest change. This is the path highlighted by the direction seen here for the gradient. And what we note is this gradient, again, is orthogonal to this level curve. It meets it at a right angle, highlighted by the tangency to, or the orthogonality, the right angle behavior to this tangent line. All right. Notice if you move on that level curve through that coordinate, that's where you experience no rate of change. That's where there's zero change in the output of the surface, is on that level curve. Orthogonal to that level curve at any point along it is the direction of greatest change. Is how we get uphill the quickest. All right? So that's the last property that we also highlight. This direction highlighted by the gradient in our previous calculation, the direction of this path through this point on our surface that leads to the top the quickest, is orthogonal to the level curve that also passes through that point. Right? It's orthogonal to it in the domain. Right? Meets it at a right angle. And I guess we could say that is a bit of the behavior that we see here, right, on our surface too. All right. But folks, that is it. That is what I want to put together for you on the gradient. We are going to use the gradient in the next set of notes I have for you that also falls into this section of material, and that is looking at the directional derivative. We're finally going to calculate some directional derivatives, which is, again, if I was on this point on my surface and I wanted to move in some other direction, some direction other than the direction of greatest change or the direction of no change, I would have to calculate a directional derivative. Right? And we're going to look at that in the next set of notes, folks. All right? So that is where we're heading. All right? This just focused on the gradient, which is slope, kind of a description, an analogous description of slope of our surfaces at any point. And it's a vector description, folks. It's a vector description that happens down in our domain. Right? And its direction is the direction of greatest change. Its length is actually how much we're changing by. Right? It's orthogonal to that level curve. It meets it at a right angle. Right? The one that passes through that point in our domain. Right? All very, very, very interesting behavior. All right? Hope you're doing well. Hope you're watching these videos. And I'm trying to tie together everything discussed in class from class to class with these videos, with your studies. All right. But with that said, we're at the 30+ minute mark here, so I'll stop here, post this up, and we'll get into directional derivatives. All right, folks. I will see you all then.